Okay, we have recently been looking at communities and how communities recover after a disruptive event, like in secondary succession, or how a community comes about initially, as in primary succession. So now we're going to look specifically at populations. And recall that a population is a group of organisms, all of the same species, that live in a specific area. A healthy population will grow and die at a steady rate unless it runs out of food or space or is attacked in some way by disease, predators, possibly even parasites. The initial increase in the number of organisms in a population will be slow because the number of reproducing individuals is small. Not a lot of adults capable of reproducing. You're not going to see that rapid an increase in growth. However, soon the rate of population growth will increase because the total number of individuals that are capable of reproducing has increased. So more adults capable of reproducing, you're going to see a more rapid increase in growth rate. This is oftentimes referred to as exponential growth, meaning that as a population itself gets larger, it also will grow at a faster rate. Exponential growth results in unchecked growth. Oftentimes, exponential growth is described as the J-shaped curve. So if I refer to something as being J-shaped, you should know that that refers to exponential. So make sure we write down J-shaped. Okay, and you can see the J-shaped curve, this being an example of a housefly population. The amount of reproducing individuals is small initially, less than 100 in the entire population, but over time, as more adults are capable of reproducing, the population's growth rate begins to spike. So exponential growth being the J-shaped curve. We will be looking at factors that can limit the growth of a population. And those are going to be things like food, disease, predators, parasites, territory. These can be living or non-living factors. So you'll hear a lot about biotic and abiotic limiting factors. A biotic factor or a biotic limiting factor would be the presence of predators. For example, an abiotic limiting factor could be the amount of available water or clean water, water being non-living. Under these pressures, these limiting factors, the population may stabilize into an S-shaped growth curve. So exponential growth having the J-shaped curve, the S-shaped curve we call logistic growth. Logistic growth is represented by the S-shaped curve. So back to the graph, you can still see the exponential growth shown in red. So we can pretend that this is the hypothetical housefly population. But when we throw limiting factors into the mix, and those listed above, disease, space, predators, food, all of these are limiting factors that are causing exponential growth to level off. And then we're going to have the S shape. So as you can see, nice S-shaped graph. The number of organisms of one species that an environment can support indefinitely is defined as its carrying capacity. Carrying capacity is unique per population. We'll go back to the graph. So this could be, like I said earlier, the housefly population. The carrying capacity would be a certain number of individuals, individual flies per the given area. It's going to be different for different organisms. So the population could probably support far more bacteria. So the carrying capacity for bacteria would be higher. The carrying capacity for deer or chipmunks or anything else is going to vary. So carrying capacity is unique per population. When a population overshoots the carrying capacity, that's when we see the limiting factors coming into effect. Deaths begin to exceed births, and the population falls below carrying capacity. So back to our graph. Limiting factors come into play. Our carrying capacity is the dashed line. Our population is falling right below that because the limiting factors are coming into play. Looking at density factors in population growth, how organisms are dispersed can be important. And there are 3 patterns of dispersal or distribution that we can see in various ecosystems. Random, clumped, and uniform. So if we look at uniform distribution, uniform distribution is when there is equal spacing between individuals, or very near equal spacing. So the example shown being the penguins nesting on these islands. They are very territorial and aggressive towards their neighbors in protection of their eggs. So a nice even dispersal we would describe as uniform dispersal or uniform distribution. Uniform is probably the least common form of dispersal. Clumped is something that humans do. So humans follow a clumped dispersal pattern or distribution pattern. Any organism that you find in herds or packs, for example, these wolves hunting in packs, are going to represent a clumped distribution. Schools of fish, don't rule out the aquatic ecosystems, probably the most common form amongst animals. Random distribution, commonly seen amongst plants, especially those whose seeds are windblown. Wherever the seed lands is where the plant grows. So a very random distribution of individuals within the population. Ecologists have identified 2 kinds of limiting factors additional to the biotic and abiotic that are related to dispersal. So previously we had talked about, or I had mentioned biotic and abiotic limiting factors, predators being biotic and water being abiotic. Now we're going to look at those factors relying on or not relying on the density of the actual population. Population density describes the number of individuals in a given area. Density-dependent factors are going to include things like disease, competition, predators, parasites, food. A density-dependent factor, its severity is increased or decreased due to the actual density of the population, hence density-dependent. For example, a population of 10 individuals in a square mile will probably not feel the effects of a parasite as strongly as if there were 100 or 200 or 500 individuals in that given square mile, same square mile. So as population density increases, the impact of a density-dependent factor also increases. If population density is low, then the density-dependent factor's impact would also be low. Versus density-independent factors, the impact is the same regardless of population density. So something like a natural disaster or a flood is going to do the same amount of damage regardless of how many individuals per given area. If there's 10 people or 10,000 people, a flood is going to impart the same amount of damage.